front row, so I guess that means that we should go ahead and start. I know that I'm probably a new face to some and not a new face to others, but I'm Rosie Johnson. I'm the project manager for the TAP program and for the PIRE project in Stewart Observatory. And we generally would like to start off the semester with an introduction and a welcome, and this is what we're working on with the TAP program outside of Colloquia, and we scheduled it a little bit late this year, so apologies, but we did want to still take the time to talk a little bit more about what's going on with TAP outside of the bi-weekly talk. So that's where we're at today. And so the first thing I wanted to do was to welcome new students. As you can see, we have quite a new solid group of students joining us from the 3 TAP member departments. And we also welcomed several existing students as official TAP members last spring. And I wanted to also mention that Dirk Human comes to us from wide theoretical experience, not from the university community at this point, but he is joining us from most recently the industry side. So just real quickly, just to keep in mind kind of the other parts or the working mechanisms of the TAP program. Outside of Colloquia, we have the steering committee chaired by Dimitrios, and with equal representation from all of the TAP departments, physics, astronomy, and LPL. The Colloquia committee, Chris, Caitlin, and Elizabeth are the people that are working extensively to invite strong speakers and to organize these talks. And then we have some theory support, some admin support in each of the departments, keeping things moving along in terms of processing paperwork and travel and setting up talks like this. I know that we probably push our website on you quite frequently with each talk, but I wanted to make sure that we directed you to the schedule that's listed. The spring schedule will be under development in the next couple of weeks. And I wanted to just take a minute to thank the steering committee and all the hosts for organizing speakers and making sure that we invite a really great representative group of speakers that represent all the TAP departments. And to just also mention that in addition to just having a variety and a good diversity of speakers from the type of work they do to demographics, we also strive to invite speakers that are in different phases of their career. We want to make sure that in addition to what they bring to us, we wanted to also portray the strengths of the TAP program at the university for speakers that are, go back to their home institutions, so that we increase the visibility of U of A's program here. So I think that's all I wanted to say about that. I wanted to mention that we are always interested in new speaker recommendations. We have a good list right now, but the form to submit recommendations is always available online. So if you hear someone or you think of another person, it's not, you don't have to wait for the email to come out to share those ideas. We can keep it fresher that way. So I wanted to talk briefly about what we did last spring. I know many of you were here, but once again, the Student Research Prize competition was announced, and Josh Lothringer was awarded the research prize for his work that was published in AppJ. And I wanted to just, is Josh here?
Graduated.
Okay, he's definitely not here. Well, thank you for that. He will be forever, his legacy will be memorialized on the wall in the physics department, and he was awarded a plaque and a small cash prize. So the next competition will be announced. It's it's every 2 years, so not until next year, late next year. The other thing that TAP does every spring is we announce matching grants. And last year was actually we had skipped a year because we had to look at available funding. So we brought the program back, and every year we've currently budgeted $6,000. Last year we received just many more applications than we anticipated, and the steering committee decided to, because there were so many student applicants, that the focus would be to distribute those awards to students. So 9 students received different levels of award depending on where they were in terms of their program. We wanted to support students that were approaching the job market, as well as some other students that had some interest in attending research or doing research, attending conferences. So the funds were, widely distributed across several different, a lot of students doing a lot of different things. And next year, we will kind of be looking again at the guidelines and how the grant money is distributed. We may also need to look at the total amount that we budgeted each year so that we can make the best use of the available funds. So that was last year. I wanted to just kind of spend just a couple minutes talking about where directions that we're headed with some other initiatives. One of the primary objectives is to, at least for TAP, is to develop large computational resources to be shared across all the departments, TAP departments that is. And along with that, we really look towards expanding some of the TAP program opportunities in addition to Colloquia and the small, the grants and the research prize. We want to talk about some other things. And then the underlying goal is always to broaden TAP's visibility across the academic community working in this area. So CK Chan has been, along with a lot of other co-Is and faculty members, is working to develop a number of proposal ideas. And I just wanted to overview those in order so that we all know some of the work that's being done and some opportunities to contribute or be involved with these grant developments. Early this year, CK submitted the CCRI proposal in response to an NSF call. That one was not funded, but along with the reviewer feedback as well as several communications with program officers, we've kind of redeveloped our focus on what calls to respond to. So that was a large funding call. We're also at the same time submitting smaller research proposals in order to develop provide additional research opportunities, but not so much to create large computational resources. So Chris Klein and Fariel and Demetrios worked collaboratively on a NASA HCP proposal that was submitted in June, and we haven't heard about that one. But again, the funding for these awards, should they be received, will be something that will support TAP research broadly across all the departments. So these are the proposals that are currently very much the focus right now. There's the NSF CSSI proposal. I've outlined the direction that this is currently headed. It's due November 1st. This is a proposal that would potentially provide large computational resources. At the same time, I'm sure most of you are familiar with the MRI program, and this is a limited competition, so we first will need to get through the university selection, and that initial proposal is due this week. These are very much in development, and so I just want to encourage anyone that has interest, ideas, or time available to contribute to these to contact CK Chan in astronomy. And that's all I wanted to say. I didn't want to take up too much of our primary speaker's time. If you have any questions, you can either contact me through email or touch base with Demetrios or CK. Thank you very much.
Thank you very much. So while we switch over laptops, I'll give our speaker her introduction. Kat Volk got her BS in Physics and Russian Studies from Wittenberg University, and then came here with her PhD, focusing on the dynamical studies of the Kuiper belt and the centaurs. She then went and worked as a postdoc at the University of British Columbia, and then has come back here and is now an associate staff scientist studying both outer bodies in the outer solar system as well as some exoplanets. I think the exoplanets you said are deferred to a later talk, and so she's just going to be discussing combining theory and observations of trans-Neptunian objects to pin down Neptune's migration history. So with that, take it away.
Thank you very much. All right. So I am going to talk a little bit about observations in this theoretical astrophysics talk, but I promise it won't be too much. So before I get into the science things I want to talk about, just a quick tour of the outer solar system so that we're all acquainted with the populations we'll be talking about. So this is a top-down view of the solar system with only the giant planets' orbits denoted here with circles. This was all of the known Kuiper Belt objects or trans-Neptunian objects at the positions of their discovery as of a year or two ago when I made this plot. We can take a side view. So it is kind of a disk-like population, but it has a lot of other features. It has significant vertical extent. And there is some realness to the pileup here just outside of Neptune's orbit, but also some of it is observational biases because the things that are closer are easier to detect. We've got a variety of kinds of orbits in the Kuiper Belt, so this is a very simplified view of it. But again, we're top down here where we just have Neptune. There is population on more elongated orbits that have been scattered into their current positions. We call those the scattered disk or the scattering population. There's also the classical Kuiper Belt that's on roughly circular, roughly coplanar orbits between about 40 and 45 AU, where Neptune is at 30 AU. So that's just some orientation before we get to the plots here. So this is eccentricity versus semi-major axis and inclination versus semi-major axis for every trans-Neptunian object, scattering object, and centaur that was listed in the Minor Planet Center as of a few months ago. There's maybe 2,000 or so known objects in the outer solar system with reasonably well-determined orbits. The lines here are lines of constant perihelion distance. So orange is coming into 30 AU, so things above that line cross Neptune's orbit. And then the blue line is 40 AU, so things out here never really approach close enough to have strong dynamical interactions with any of the known planets anyway. We're going to zoom in because most of what I'm going to talk about is the structure of relatively nearby portions of the Kuiper Belt. So here we're getting into being able to see some of the substructures. So again, these are observed objects, so there are biases in these plots, but it's still illustrative of the populations that we know are there even when we take into account the observational biases. So there's these dynamically cold, circular, roughly coplanar Kuiper Belt objects, and it's the same set of objects that have the relatively low eccentricity orbits that also have relatively low inclination orbits. That's dynamically important because most people think those formed where we see them today, so they're probably some remnant population of the planetesimal disk that the giant planets formed in and interacted with. Then, of course, we've got the dynamically hot populations that have elongated and inclined orbits that are kind of spread out, and they also have quite large inclinations. I'll note that this goes up to 50 degrees, and that's an arbitrary cutoff, just that we could see some of the structure. There are even some retrograde orbits in this extended dynamically hot population. And then we have the resonant population, so things that are in mean motion resonances with Neptune that pile up at specific semi-major axes. I've highlighted here the three most populated in terms of things we've seen. So the 3-to-2 resonance with Neptune, which Pluto is in, the 2-to-1 resonance with Neptune, and the 5-to-2 resonance with Neptune. And we'll come back to those specific resonances a little bit later in the talk, but that's just a very small, visually apparent subset of the resonances. There are, I didn't actually count, but probably 20 or 30 resonances would be my estimate that have identified observed objects in them. So there's lots of objects in resonance with Neptune. So the main question we're trying to answer is how did we get all of this structure there in the outer solar system? We have our typical picture where everything should have been relatively dynamically cold and kind of boring, and instead we have this huge diversity of orbits in the Kuiper Belt. And some of the structures, you could populate today, like this scattering can happen as things slowly dynamically leak out of the classical belt. They can interact more strongly with Neptune and scatter out, but there's other things that we need a more dynamic picture of the solar system to generate, like these pileups and all these resonances. So this is related to how we think the giant planets formed. So, in the early solar system, we think the giant planets formed in a more compact configuration, probably inside 15 to 20 AU, so inside where Uranus is today. And then they migrated to their current positions, listed here in semi-major axes. So they got there by interacting with the planetesimal disk that was left over after the planets formed. So you have the compact configuration, you have a massive, let me think, maybe roughly like 30-ish Earth masses of material in a planetesimal disk here. And when you have that kind of configuration, of course, the gravitational perturbations from the large planets is going to cause some excitation in the planetesimal disk, and then they will end up exchanging energy and angular momentum. And so this is just a typical movie I borrowed off of somebody else's website, because I don't make movies, of what happens when you embed large planets in a disk of massive test particles. So these things don't interact with each other, but they do have mass and they interact with the planets. And when you let them go, you get reorganization of the giant planet system. And you get the planets spreading out and this outermost planet migrating into the disk and scattering all sorts of stuff around. And you can start to see how that leads to much richer dynamical structures. So we want to basically try to take what we have left over from this planetesimal disk and try to use it to constrain the details of what happened during that migration process. So I'm going to talk to you about a couple different approaches to trying to constrain this. Starting with, why do I focus on the resonant objects, the resonant populations, in trying to constrain Neptune's migration? But then once you start thinking about the resonant populations, you have to think about what is primordial, captured during that planet migration process, versus what is transiently and resonant today, which I'll talk about. And then talk about a project where we were modeling, fairly what we think of as simple piece of the migration story, and finding out that it's still pretty complicated, even when you break it up into what we think should have been a fairly relatively easier to understand piece of it, and then talk about a couple ongoing and future projects. But first, why the resonant TNOs? So just as a reminder, orbital resonances occur when you have period ratios that are in a simple, periods that are in a simple ratio to each other. So this is an image top down of the solar system. We're in Neptune's rotating frame, so we're sitting and rotating at the same orbital frequency as Neptune, and this is the path Pluto follows in that frame. So Pluto completes 2 orbits for every 3 orbits of Neptune going around the Sun, and that means, since it's in the stable resonant configuration, it comes to perihelion about 90 degrees away from Neptune, and this is a stable configuration. It's kind of like a pendulum. So Pluto's not always exactly 90 degrees away from Neptune when it comes to perihelion, but if its orbital configuration drifts so that perihelion happens a little bit closer to Neptune, it gets pulled back to the 90-degree point. And we have this amplitude of libration that's similar, can be modeled, in fact, with a simple pendulum model. So Neptune has a lot of these resonances, and Neptune's resonances happen to be stable. So they are places where you can collect bodies, and that's part of why they're so populated. But the main reason why they're so populated is that as the planets are migrating, as Neptune migrates outward into the planetesimal disk, its resonances also have to migrate outward, because resonances occur at fixed semi-major axes because it's a period ratio, and the periods are just set by the semi-major axes of the orbits. So if Neptune's semi-major axis is increasing, the associated resonant semi-major axes are all increasing, and when that happens, you can grab objects into resonance. So this is kind of the traditional picture of smooth, kind of orderly planet migration. So this is a figure from one of Renou's very early papers on this topic, with the idea that as Neptune is migrating outward, the 3-2 resonance, which Pluto is in, migrates outward. It can pick up Pluto, and as Pluto then gets dragged along by the rest of the migration happening, its orbit becomes elongated as it's dragged along in the resonance. And this can happen in a lot of different resonances, so I've just plotted a couple here. This is a fairly typical kind of smooth migration configuration where you're moving Neptune about 7 AU outwards, and so the resonant locations will also move. But that's, and when you simulate this with a whole disk of test particles, you get lots of stuff piling up into a lot of Neptune's resonances. So for example here you can see all the stuff that gets picked up into the 2-to-1 as Neptune migrates out to its final location here. And the fact that the 2-to-1 is really good at picking up stuff will come back later in one of my observational projects. So, now there are complications that you could put on top of this generally smooth migration process. Now, of course, this is happening by actual individual scattering events with planetesimals in a disk, so you wouldn't actually expect it to be perfectly smooth. If you add in things like graininess to the migration, where you simulate what would happen if Neptune was scattering a bunch of Pluto-sized things. So instead of just kind of slowly marching out due to a bunch of interactions with small bodies, it's having these more discrete jumps. Then that adds a graininess to the migration, and that affects what good you are at picking up objects into these resonances as they migrate. If you truncate the planetesimal disk at a certain heliocentric distance, then some of the resonances don't have anything to sweep over, and that affects their final distribution. So the distribution of all the things that get captured into all of Neptune's different resonances should tell you something about the details of this process. And then, of course, there's even more variations in the migration story that you could have. So, like, this is an early iteration of the Nice model, the kind of classical Nice model, where you have Jupiter and Saturn crossing their mutual 2-to-1 resonance, causing planet-planet scattering to occur. The specific orbital history does not work for what we know about the giant planet orbits, but the idea that you could have a more violent process where you actually have, Uranus and Neptune scattering off of each other or off of Saturn, and thus giving you a very different picture of how the planets arrived at their current configurations, is still a valid idea. And that gives you very different pictures of what gets captured into the resonances. So these are just two different papers a decade apart predicting kind of how many things you should find in some of the resonances versus right next to some of the resonances, depending on exactly how these planet-planet scattering events go and how the post-scattering eccentricity damping goes. So it just is telling you that there's a lot of detail about the migration to be found in these resonant populations, because how many things you put in which different resonances really depends on the details of the migration history of the giant planets. But first, if you want to make a model of what happened during planet migration, and then say something about what got captured during planet migration, you have to be able to take the observed populations today and know which of those observed populations are going to be primordial, so still left over from that planet migration process, versus what might be a transient phenomena in the current solar system, because we know that there are objects in resonances today that are short-term resonance. So we need to know what populations we're looking at if we're going to compare the predictions of how we got from point A to point B to the observations. So this is an example of, you have all these objects that are scattering, that have these perihelia between about 30 and 40 AU. And it's basically a random walk in semi-major axis. When they come to perihelion, they can get either a strong or a gentle kick from Neptune or the other planets, which changes their orbital energy, which changes their semi-major axes, and they random walk kind of in this fan pattern. And as they random walk, they can encounter some of these weaker, more distant mean motion resonances with Neptune. So this is a test particle that starts off on a scattering orbit near 100 AU, random walks a little bit, spends some time here stuck to the 11-to-2 resonance with Neptune, random walks some more, gets stuck for a few million years to the 5-to-1. You can see this in lots of different parts of the solar system. We know there are temporary co-orbitals with the giant planets a little bit closer in, and there are lots of temporary sticks in the scattering population. So in particular, some of these more distant resonances, you can almost see some vertical structure in the plot here. They are particularly sensitive to the structure of the disk when the planet's migrated if they're primordially captured. But they're also easy to populate in a more transient fashion. And sometimes transient is a relative term. So this is just a figure of all of the resonant objects that were detected in the Outer Solar System Origins Survey, which I was a collaborator on. So you can see that there's a huge number in wide range. This is a log scale and semi-major axis. But let's just take a look at the two most distant resonant objects that we detected. So there are two objects we detected in the survey that are in the 9-to-1 resonance with Neptune at about 130 AU. And that's a little puzzling. That resonance is pretty far from Neptune, so don't really think there could have been a disk for it to sweep while Neptune was migrating. It was probably beyond what the original disk was. So we wanted to take a look at, what maybe these objects are one of these transient populations that are just stuck while random walking. So we took a look within the orbital uncertainties of these objects. What's the median amount of time that if you start a numerical integration today with their current positions relative to Neptune, how long do they stay in the 9-to-1 resonance with Neptune? And it's about 1 billion years. So some fraction of them, about 15 to 20% of the clones of each object stay in resonance for 4 billion years, which would be consistent with them being primordially captured into the resonance. But the majority of the clones have shorter lifetimes. But 1 billion years is still a long time. So that's what I meant about relative. You can't just look at the very short-term behavior and tell whether something you're seeing is a resonant object that was captured early in the solar system or something that's stuck temporarily, because temporarily can be quite long. So we decided we needed to take a look at modeling this transient population, try to identify what are the resonances that are most likely to be filled by transient things out of the scattering population versus resonances that are not populated by transient things. So what we did is we took a model of this scattering population and we integrated it forward in time for a gigayear and tracked all of the times those actively scattering test particles stuck to Neptune's different resonances. We analyzed not only what resonances they stuck to, but how long did they stick to each of the resonances. And this is work, the analysis was led by Matthew Yu, who was then an undergrad student at UC Santa Barbara. He's now a grad student at UCLA. So he wrote some nice code to go through all of this output from the simulations and identify each resonance stick by looking at this librating resonant angle, identifying which resonance it was and exactly how long it stuck in that resonance. And we were able to build up a picture of how much time things in the scattering population spend in different resonances with Neptune. So we built up this picture. So this is the resonance ratio. So this is the 2-to-1 resonance, 3-to-1 resonance, 4-to-1, and so on. And then this is the total number of orbital periods that particles in the scattering population spent in each of these resonances. And we were able to reproduce some of the earlier findings that work on transient sticking. These n-to-1 resonances are the stickiest resonances in the scattering population. So objects stick to them quite often, and they tend to spend a little more time in them when they do stick to them. The next stickiest resonances are the n-to-2. So you can see these, at the half integer. And then it just goes on from there. And you can actually use that kind of picture to build up a predicted population of how many things of a certain size should we see in each of these resonances, just as a function of transient sticking. So we selected, we did a whole bunch of resonances in the paper, but here are the ones that have observational, real observed objects in the resonances. And we can predict how many things should be transiently stuck based on our estimate of how many objects are in that scattering population. So you can see here that the n-to-1 resonances in particular should have many objects bigger, brighter than absolute magnitude 8.6, which is roughly 100 kilometers for typical albedos. And then we can compare that to observational estimates and how many things we think are in these populations. So we have, we take our observations and we basically debias them to get a population estimate. And we know, for example, there's about 4,000 objects in the 2-to-1 resonance. So compare that to 65 from the transient population. So we're pretty safely observing a primordial population here. And the same thing for many of these other resonances here. We don't have population estimates for the 4-to-1 or 6-to-1, but the 5-to-1 certainly has a lot of objects in it compared to the predictions. So these are things like those 9-to-1 objects. So we think we can identify this way, look, what resonances are reflecting that primordially captured population. So that's good, because now we know what our data set is telling us. It is telling us something about the early solar system. The majority of the things we see in these distant resonances probably were captured early in the solar system's history. So on top of, when we see a new object, we can integrate its orbit and try to figure out is it stable or not. But we can also say that when we build up our statistical picture of resonances like the 2-to-1 and the 3-to-2 and the 5-to-2, which we have good observations of, we are looking at a primordial population. But it doesn't necessarily make it much easier to figure out what that's telling us about the migration story.
Before you go on, can you
Yeah.
go back to this? Can you say a few more words about, do you have any intuition for why these numbers sort of shake out the way they do?
For the predicted,
Yeah, for the predicted. So, for example, why is the 6-to-1 so much better than the 4-to-1? Is it just that you get?
it's a time weighting. So as you go out in semi-major axis, the orbital periods are getting longer, and the libration periods within the resonances are getting longer. So yes, there's a lot of interesting dynamics. We made some analytical estimates of the libration periods, and it kind of maps with the predicted numbers. So you tend to stick maybe for roughly equal numbers of libration cycles when you stick, but the libration periods get longer for those more distant ones, so it turns this is a time-averaged population. It's still to be confirmed, and it's one of ongoing projects is to better understand that sticking process, because we know our analytical estimates of the libration periods are not really correct, but they're roughly correct, and it roughly tells the story, and so it's tied to that, but still under investigation. Okay, so if we take those primordial populations, what can we tell about Neptune's migration? So when I said I was going to look at just a very simplified picture of the migration scenario, I really do mean simplified. We are taking a situation where we have the giant planets in their early, more compact configuration and a truncated, massive planetesimal disk. So these in my simulations are just going to be represented by test particles, but they're cut off at Neptune's current semi-major axis. So we're just looking at one part of the resonance capture process. So you can sweep over an existing disk out here to pick up objects in resonance, but you can also scatter things out to then be swept up into resonance. So we are only looking at the piece of the problem where we're scattering out, so creating a very dynamically hot population of objects to then get picked up into the resonances, to then become the observed TNO populations. And the reason we're looking at this simplified picture is because there was this interesting paper in 2015 that found in this scenario, where you have a truncated planetesimal disk, you could explain the large inclinations of the observed Kuiper belt objects if you just migrate Neptune slowly to its current position. So we're ignoring any planet-planet scattering, we're ignoring graininess, all those other possible complications. And because one of the really tough things to reproduce in any of our migration simulations is these really large orbital inclinations. I mean, the kind of median inclination in this hot population, it might be as high as 20 degrees. And it's really hard to create that from planets that are roughly coplanar. Neptune has a very small inclination today. So this has been a problem in a lot of our migration simulations to pump these inclinations up enough to explain the observations. So this was a really interesting result. He in particular found really strong evidence in this 3-to-2 population, where there was a really strong timescale dependence. So if you scatter things out and then capture them into the 3-to-2 as Neptune arrives at its final location, if you do it really fast, e-folding timescale of 1 million years to go the 5 to 7 AU to get Neptune out to 30, then you get a really low inclination, almost nothing above 10 degrees out of the plane. If you go to 10 million years, the peak is at about 10 degrees, and then if you go to 30, the peak's at almost 20 degrees. So he found this really strong trend in his simulations, and he published this paper claiming this is the evidence that Neptune migrated really slowly. And he did tests to try to see if this was something to do with his initial conditions, and it looked like a robust result. So that left me puzzling, because I had done some very similar simulations and had found no such correlation with migration timescale in my simulations. So those original simulations aren't shown here because they were pretty bad in terms of number of test particles, but we redid the simulations with more test particles using the HPC. And this is our same inclination distributions with the migration timescales color-coded. So our short migration timescale here did have the lowest peak inclination, but it had a really long tail out to large inclinations. Our hottest inclination distribution for the Tinos ended up being a 10 million year migration timescale, so Nesvorny's 10 million year peaked over here. So basically there's no trend here in the migration timescale and the inclination distribution we're seeing in the Tinos that we capture out of simulations with essentially the same initial conditions in terms of where the planets are and the test particles.
What are the dark dotted lines?
Thank you. The dark lines are observational constraints on the intrinsic inclination distribution for the Tinos. So anything kind of in between this kind of more modest inclination distribution and this quite puffed up inclination distribution is consistent with our observations of this population. So basically my simulations are saying, well, any of these migration timescales is close enough to the observed population that's fine. So you wouldn't conclude anything about migration timescale based on these simulations. So we really started to try to dig into why is this result. It seemed so strong in Nesvorny's paper. It was a very clear trend in his simulations. So why did our simulations not show this same result? And it turns out to be, we are pretty sure, because of secular dynamical effects that depend quite sensitively on some assumptions you make in simplifying the problem to make it tractable. So just a quick reminder, so the inclination is the tilt of the orbit to the reference plane, but it's not just a tilt, it's also a direction of where that node is crossing the reference plane. So you can kind of think of it as a vector pointing out of the orbital plane that's described by this tilt and the location of that ascending node. And we can describe how that should evolve over time due to interactions with other massive bodies in the solar system by taking a secular approximation. So secular approximation is where instead of considering the planets to be, point masses in their orbits, we're going to take their masses and spread them out into rings. And those massive rings will perturb each other and evolve in time. For orbital eccentricity, what this results in is a precession of the direction of pericenter, and for inclinations, this results in a precession of the longitude of nodes and a kind of wiggling back and forth of the amount of tilt. So here in this image, black is above a reference plane, gray is below, and if you set our giant planets as they are today and make this secular approximation and say how should their orbital inclinations evolve, they basically just precess and wiggle around. And that's a very well understood, and it describes our solar system, the inclination evolution, quite well. So this is for the planets. So these things that are getting captured into the resonances are small bodies. You can think of them as massless. They don't really, after migration anyway, obviously they affect the planets, they're causing the migration, but on the whole, any individual test particles orbital inclination is going to be set by what the planets are doing. So the test particles that are out here beyond Neptune's orbit have a kind of natural precession frequency that's due to the net effect of all of the massive rings of the planets. But each one of these planets here kind of has a dominant, at least in our solar system, a dominant frequency at which it precesses. So if you have a test particle out here, out past Neptune, that's natural precession rate happens to match one of these frequencies of the giant planets, you get what's called a secular resonance, where you're forcing at the same, forcing at the natural frequency of the test particle's orbit. And that's very apparent in the Kuiper belt, because I've shown this spot a few times without really talking about this gap in here. So this is a real gap. There are no low inclination Kuiper belt objects between about 40 and 42 AU from in semi-major axis. And that's because that semi-major axis range is where you get one of these secular resonances, where the natural precession frequency of the Kuiper belt object's orbit matches roughly Neptune's precession frequency. This is actually true for both the nodal precession and the longitude of perihelion precession. So there's two secular resonances happening here that clear out any test particle on quite short time scales. And I'll just note that the 3-2 resonance is very close. The 3-2 is at 39.5 AU, and the secular resonance is about 40 to 42 AU. So they're quite close together. And so this is the first hint of what might be different about our migration simulations and Nesvorny's. And then that's kind of confirmed when we look in detail at a couple time histories in our simulations. So this is one particular test particle from one simulation that is going to get captured into the 3-2 resonance as Neptune is migrating. So it's starting off here. It is scattering around in semi-major axis because it is having direct gravitational scattering events with Neptune. But then it gets scattered out beyond the 3-2 resonance, and then the 3-2 resonance catches up with the orbit, and then it gets captured into libration in the 3-2 resonance. And if we look at what's happening to the inclination here, early in the simulation where the object is just scattering around, its inclination is basically just jumping around a little bit within a few degrees in response to these direct gravitational scatterings. But then once it gets scattered out beyond the 3-2, it smoothly increases from very small to 16 degrees or so here, before effectively getting stabilized when it gets picked up by the 3-2. And this is exactly what you'd expect. This kind of sinusoidal smooth increase in the inclination is what you expect when you're near one of those frequencies where you're getting a strong forcing of the inclination. So because of the location of that particular secular resonance, it happens to be just outside the location of the 3-2. This secular excitation is really important in setting the final inclination distribution of all the particles that ended up captured into the 3-2 in the different simulations.
Can I ask a question?
Yeah.
Why didn't it looks like it went past that resonance and then it came back?
So when it's still at a perihelion distance where it can scatter off of Neptune. So this is still just some random walk due to direct gravitational encounters. So yeah, the efficiency of capture is extremely low because of that. So I think to end up with a simulation, to end up with about 100 to 200 test particles in the 3-2 at the end of the simulation, you have to start with 200,000 test particles. So it's a very inefficient process, and that's because when they get scattered out here, the 3-2 has to catch up with them before they get scattered away again. So there is a lot of orbital changes going on because of that direct scattering. So it's only the ones that are lucky, basically, that get picked up into the 3-2. So, but that secular resonance is really important because we took a look at our original simulations here that showed no dependence on the migration time scale. And one of the things we noticed in looking at the inclinations of the planets was that in these simulations, Neptune's inclination was a little bit enhanced relative to its current inclination today. And the strength of the secular interaction in these secular resonances is a function of the inclinations of the planets. So you're doing these migration simulations and the planets are interacting with each other as you're artificially migrating them. So it's difficult to arrive at the perfect final eccentricities and inclinations. So we decided to check this. We went back and we brute force did a bunch of just planet migration scenarios until we found some where the planets ended up with slightly lower inclinations than they have today, so suppressing the secular effects. And when we then added the test particles to those simulations, we get lower Plutino inclination distributions. So if you have a strong secular resonance that can pump up inclinations, you get wider inclination distributions. If you have a weaker secular resonance that's not as good at pumping up the inclinations, you get colder inclination distributions. Now, what sets the strength besides just the inclinations of the planets? The location of that resonance is sensitive actually to what Uranus is doing in the migration simulations, because the forced or the kind of natural precession frequency that you get out of the test particles depends on all the planets. So if you just have a slightly different kind of time history of where Uranus and Neptune were relative to each other, you can enhance or suppress this effect by moving the secular resonance a little bit. The inclinations go up and down, that can suppress or enhance the secular resonance. We're ignoring here that that is a massive planetesimal disk we were starting with, and that would also affect the secular structure. So unfortunately, it's really complicated. Even when we're taking this, what should have been a pretty simple piece of the puzzle, we're just doing smooth migration. We're not considering graininess. We're not considering scattering planets that adds all sorts of other effects. But we're still getting divergent results, probably based on small differences in the simulations. For example, in some of Nesvorny's simulations, he damped the inclinations of the planets to arrive at their final inclinations, whereas we chose not to do that in our simulations. So all the simulations have to be simplified because even doing it in this simplified manner takes hundreds of thousands of CPU hours. So we just have to be cautious that those simplifications can matter. So that brings me to some of the other projects we're working on to try to address this problem.
I have a question.
Mm-hmm.
Is this a valid also for the eccentricities?
Yes. Yeah, I'm ignoring that. But yes, so there are similar, especially because there is that eccentricity secular resonance that's in about the same area as the inclination one. So yeah, that is also an important piece because the eccentricities also affect the capture probabilities. So yes, but even for the inclinations, it's already very complicated. Okay, so one of the other ways we're trying to tackle constraints on the migration problem, because I'm a little worried that our numerical simulations are going to be tricky to draw robust conclusions from in some of these details, like the detailed structure of the resonances. But we can also look at the physical properties of the observed objects and try to see if that's telling us anything about the migration process. The OSIS survey discovered about 800 Kuiper belt objects in a very nice characterized manner. Then we had a follow-up program on Gemini getting the photometric colors of the brightest 25% of these objects, because that takes just as much time as discovering. So colors on 200 objects takes as much time as discovering 800, because they're very faint. So they found some interesting results. In particular, Rosemary Pike in 2017, using the Colossus data, was able to show that these cold classicals, which remember we think are a remnant of that original planetesimal disk, so these are things between about 40 and 45 AU, they have distinct surface colors if you look at them in R minus Z and G minus R. We don't, they're all redder than solar. These are basically just a different kind of red than the dynamically excited populations, but they do fall out in a statistically distinct grouping. And we don't know what that means, but presumably it means something about their surface compositions. And maybe there's something distinct about this remnant of the original planetesimal disk versus this excited population that we think got scattered out from closer to the sun. So there's reasons to think they might have slightly different ices because they're forming at different temperatures. But the important thing is we have a surface color tracer of things that belong to this particular heliocentric distance range. So remember I said in one of those early slides that this 2-to-1 resonance, which happens to be just outside this cold classical belt, it's at the outer edge of the cold classical belt. If that 2-to-1 resonance migrates through this population in any kind of smooth manner, it is really good at picking things up. So it is very efficient at picking things up into the 2-to-1 resonance. So if we have this population here in this nice dynamically cold disk that have these distinctive surface colors, if the 2-to-1 migrated smoothly over that cold classical population, these surface properties should be seen inside this resonance. And we can actually do dynamical simulations of that capture process, and we can ask, so if we make an unbiased observation here of the color distribution in the 2-to-1, and we can constrain how many of these cold classical-like surfaces are in the 2-to-1, what does that tell us about migration? So we have an ongoing program at LBT because these things are 24th magnitude to 24.5. So that's what it takes to even get colors on them. So far, we have not seen any cold classical surfaces in the 2-to-1. So we already think that rules out smooth migration of the 2-to-1 over this population at kind of a 90% confidence level, but we're still processing data from our other runs. So I think that's going to be a really nice constraint so that we can go back to our dynamical models and have a little bit better of an anchor point. We'll at least know to better precision what one resonance was doing. And then maybe we can pin down what are some of the other important effects to look at the more distant resonances and take another look at the 3-to-2. And then just really quick, I'm almost out of time because I do want to leave some time for questions, but just want to mention that sometimes these objects from the outer solar system come to us in the form of comets and centaurs in the inner solar system. And if we really want to learn what they're made of and do some comparisons with the planetesimal disk that we think they formed out of, there's a real benefit to visiting them with spacecraft. So we have here the New Horizons flyby of a cold classical Kuiper belt object. So maybe we'll actually get to know what those surface colors mean when they get all the data back from New Horizons. And then for comparison, 67P visited by Rosetta. But we don't really understand. We have a lot more data on these comets than we do about Kuiper Belt objects. But we don't entirely understand how the physical processing happens that gets them from this pristine state to their really highly evolved state. So I just want to do a shout out that there is an object in the solar system that we could go visit that would be perfect for understanding this process. And it's in this in-between population, the centaurs. There's one of them that's in a nice circular orbit that's easy to understand, just outside Jupiter's orbit, 29P Schwarzmann-Bachmann 1. And it's this really funky object. It outbursts every 60 days, throws off a lot of material that would be really nice for sampling with a spacecraft, get an understanding of what these things are made of, and how the early stages of activity can turn you from a New Horizons target into a super highly processed comet. And it's dynamically important. I don't have time, but you can read our recent APJ Letters paper about why this is a really important orbit for transitioning. But I just want to shout out for our Discovery mission proposal to go orbit 29P SW1. That was just put in July. And it would really help us understand how the evolution of the solar system went down if we could go visit one of these transition objects and get in situ data. That would really help inform our theory. So it's a Walt's mission. So if you've seen Walt looking tired, that's why. And it's really exciting. So with that, I just want to leave with some final thoughts. So how planet migration and planet formation happens and affects the Kuiper Belt is really complicated, and we really have to look at this from a bunch of different angles. Because apparently, even though when we think we have a pretty good constraint, sometimes little tweaks can cause that to end up not being a great constraint. So we need multiple attacks of the theory, multiple attacks of the observations to really constrain this process. So thank you.
Questions?
What is the development timescale for secular excitation that you show in your simulation?
So for that particular secular resonance, it's typically 1 million to 2 million years. So the precession frequency that you're resonating with is 1.5 million years, I think, for the inclinations. So it's very fast, especially for outer solar system timescales. So you don't have to be near that resonance for very long to get your inclination pumped up. And that's why it's all cleared out when we look at the observational picture. You know, you can't be in that secular resonance for like 10 million years. Within 10 million years, you'll be pushed to higher inclinations and higher eccentricities that'll cross Neptune's orbit. So might not be fast if you're used to asteroid belt standards, but 1 million years is super fast by Kuiper Belt standards.
So you showed this gap at around 40 AU for inclinations and due to a secular resonance. I was curious, it wasn't clear to me from the data. Do you see anything on the eccentricity side of it?
Not a gap, because once you get up to high enough, let's just go back to once you get up to high enough inclinations, you can avoid both secular resonances. So I give a very simplified picture from linear secular theory where eccentricity and inclination are decoupled, but in reality they are coupled once you get up to high enough E and I. So you mostly see this gap at low inclination, because once you're above about 10 degrees inclination, the eccentricity secular resonance isn't at that location anymore. So that's why you see the gap very clearly, but there's not much of a feature in the eccentricity. I mean, there's fewer things there, but that also is because of other dynamics.
Does gas drag potentially play a role at the earliest phases, or is this much later after all the biggest gas has dissipated?
It depends who you ask. So, but yes, probably it does matter. So if migration happens really early, then there could still be some gas drag. So yes, that could be a factor, and it certainly could affect the locations of the secular resonances. Probably most of the migration is slow enough that it happens after the gas is gone. You know, because we think a typical timescale might be several million years for the planet migration. You've got to form all those planetesimals first. So probably it's not hugely important, but it could be important in the early stages. And maybe migration happens really fast. but that would probably damp things, so it might make the problem worse to try to explain these really excited orbits if there was too much gas around. But that's another thing we typically ignore when we do the modeling.
Any other questions? If not, let's thank the speaker again.
Thank you.